Welcome back for a second example of solving a Bernoulli differential equation. For a quick review, a Bernoulli differential equation fits this form here, where n, the exponent on y, is any real number. Hopefully we recognize that if n is equal to 0 or 1, we would have a linear first order differential equation. So for this video, we'll be looking at values of n that are not 0 or 1. And to solve a Bernoulli differential equation, we perform a substitution using the formula v equals y raised to the power of 1 minus n. By performing this substitution, the resulting differential equation will be a linear first order differential equation, which we'll solve using an integrating factor. Once we solve for v, we'll then go back and solve the original differential equation. So let's take a look at our example. First, we need to recognize that the given differential equation is a Bernoulli differential equation given by this form here, but it's not quite in the correct form. We want this first term to be y prime or dy dx. So we can either multiply every term by 1 over x or divide by x to put this in the correct form. So this would actually be y prime plus, I'm going to write this as 1 over x times y to make it fit the form we're looking at here, equals, I'll write 1 over x times y to the power of negative 2. Notice in this form, it fits perfectly with the form here in red. Next, we should recognize that n, the exponent on y, is equal to negative 2. So if n is equal to negative 2, using this formula here, v is going to be equal to y to the power of 1 minus negative 2, which would be y to the third. Now if we take a look at the differential equation, we need to perform a substitution for y here and here, but also for y prime or dy dx. So we want to solve this equation for y. So if we take the cube root of both sides, we would have the cube root of v equals the cube root of y cubed. So we can say that y is equal to v raised to the power of 1/3. This is going to be the more helpful form because we have to find dy dx now. But to find dy dx, we are going to have to apply implicit differentiation because we want dy dx and we have y in terms of v. So y prime is going to be equal to 1/3 v to the 1/3 minus 1 is negative 2/3 times dv dx. Again, we're applying the chain rule here because we want the derivative of y with respect to x, not just v. So now we'll use these two equations here to perform our substitution into this differential equation here. So y prime is just all of this plus 1 over x times y, where y is v to the 1/3, equals 1 over x times y to the negative 2. Well, if y is v to the 1/3, v to the 1/3 to the power of negative 2 would be v to the negative 2/3. And now that we perform this substitution, this is now a linear first order differential equation. And now that we performed this substitution, the resulting differential equation is a linear first order differential equation, or differential equation in this form here. But notice how the first term needs to be dy dx, so now we'll have to manipulate this to make it fit the form. Let's do this in two steps. Let's first divide everything by v to the negative 2/3 power. This simplifies to 1, so we have 1/3 dv dx plus, here we subtract the exponents. 1/3 minus negative 2/3 is just 1, so we have 1 over x times v to the first, or v, equals, this simplifies to 1 as well, so we just have 1 over x. Now there's one last thing we have to do here. We need to multiply everything by 3 in order to have this first term be dv dx. So we'll have dv dx plus 3 over x v equals 3 over x. Now that it's in the correct form for a linear first order differential equation, we'll now multiply through by the integrating factor, which is mu of x equals e raised to the power of the integral of p of x dx, where p of x is the function being multiplied by y, or in this case, the function being multiplied by v. Let's go ahead and do that on the next slide. Again, to find the integrating factor, we need to recognize that p of x, in this case, is going to be the function 3 divided by x. So our integrating factor, mu of x, is going to be equal to e raised to the power of the integral of 3 divided by x dx. I'll go ahead and factor out the 3. So we'll have e raised to the power of 3 times natural log x. This is going to simplify. We can move this 3 to the exponent position. So we have e raised to the power of natural log x cubed, which simplifies very nicely just to x cubed. So mu of x is equal to x cubed. Remember here, when this base is e and we have log base e, it simplifies to the number part of the log. Now we're going to multiply both sides of this differential equation by x cubed. So we'll have x cubed dv dx plus multiplying by x cubed, this will simplify to 3x squared v. This will simplify to just 3x squared. Remember, when solving a linear first-order differential equation, the left side of this differential equation, this side here, is always equal to the derivative of the product of the integrating factor and y, or in this case, v. So this is equal to the derivative of our integrating factor x cubed times v. And we can easily verify this if we apply the product rule to this derivative. But because it's equal to the left side, it's also equal to the right side, so we can say this is equal to 3x squared. And now we can solve for v if we integrate both sides of this equation with respect to x. On the left side, the integral and the derivative undo each other, so we're left with x cubed times v must equal, integrating here, we'd have 3 times x cubed divided by 3, or just x cubed, plus c. And now we'll divide both sides by x cubed to solve for v. So we have v equals 1 plus, this would be c times x to the power of negative 3. But remember, we're not done. We're trying to solve for y, not v. So let's finish this on the next slide. Way back on the first slide, we said that v is equal to y cubed. So if v is equal to y cubed, we can say our solution as an implicit equation is y cubed equals 1 plus c times x raised to the power of negative 3. This would be the general solution to the Bernoulli differential equation. And to show this graphically, the given differential equation would produce the red slope field, and then from our implicit equation, if we selected the following values of c and then graphed the functions, each of the functions on this slope field represents one of the possible solutions from the family of solutions or from the general solution. Okay, I hope you found this helpful. We'll take a look at one more example in the next video.